So this lesson is going to be on the last lesson in logs, which is called solving logarithmic equations. And it's on page 259 of your workbook. Before we do the questions in this lesson, though, I want to do these two questions here. So you could just jot these down on a separate sheet of paper. So when we're solving log equations, it's exactly like it sounds. We're going to have a log and an equal sign. And then essentially you're going to be solving for the unknown variable, which is going to be, in all of these examples, it will be x. These two questions would actually be fair game questions for what you've already done. So we'll solve these two sort of as a review, and then we will get right into the lesson. So what you do is if you're in log form, to get out of log form, you have to go to exponential form. So you'd write 5 to the power of 25 is equal to 125 times x. So the base raised to the answer is equal to the argument. Now we are in exponential form. How you do solve an exponential equation? If you get the same bases, you could drop your bases and equate your exponents. So I need you to rewrite 125 as base 5, right? So we're going down to base 5. So that would be 5 to the power of 25 is equal to 125 is the same thing as 5 to the power of 3, and that is times x. If we are solving for x, you need to isolate x, get it alone. So get rid of this multiplied by times to the 5, multiply the opposite of times 5 to the power of 3 is dividing both sides by 5 to the power of 3. This, where I got this question, was an old diploma, and it was a multiple choice question. What they wanted you to do is they wanted you to stay in base 5. So all of the answers were base 5, and then you had to select the correct exponent. So once you get to this step here, you are in exponent laws from 10C. Bases are the same, and you simply subtract the exponents. So 25 minus 3, the answer was x is equal to 5 to the power of 22. And then that would have been one of your choices for multiple choice. Okay. This one, we're going to set it up the exact same way. This question was also a multiple choice question, and it said solve it to the nearest hundredth. So I want you to start setting it up, right? Get out of log form by going into exponential form. So you always take the base of the log and raise it to the power. The answer becomes the power. So x plus 2 to the power of 10 is equal to 5. We need to eventually get this x by itself. So I need to get rid of this to the power of 10. So how we get rid of that? What can you multiply this by to get rid of that? You can multiply it by the reciprocal, which would be 1/10. If I raise this to the power of 1/10, I have to raise this guy to the power of 1/10. And then what happens is this becomes 10 over 10, which is just 1. I would be left with x plus 2 is equal to 5 to the power of 1/10. And then to solve for x, I need to get rid of that 2. So subtract 2 from both sides. X would be equal to 5 to the power of 1/10 minus 2. And then because it says solve to the nearest hundredth, you know that this is going to be decimals, and that becomes a calculator question once you get to this step here. So you would take out your calculators, and you would type in 5 to the power of 1/10. And then minus 2. So the answer is negative 0.8, nearest hundredth would be 2 decimal places, so negative 0.83 would be your answer. The other way that you could have entered this on your calculator is, remember 5 to the power of 1/10, that could be written as the 10th root of 5 minus 2. So if you would have entered that on your calculator, you would have gotten the exact same answer, right? So the 10th root of 5 and then minus 2. And you get that exact answer. Okay, so that's how we solved logs in the first chapter of exponents and logs. What we're going to do now for this lesson is we're going to make it slightly more complicated than this. So in your exam, you will see questions like this, and then you will see questions that I will show you from this lesson. So what is going to happen in this lesson is there's going to be two cases, and I'm going to call this first one, I'm going to say this is called case one, and the second one I'm going to call case two. And you just have to be able to look at it and say, is this going to be a case one or a case two? So what case one is you're going to have an equal sign, and you're going to have a log on both sides of the equal sign. Okay, so you only have logs. You don't have any constants, like Q here would be a constant. So case one is you have one log on each side. And if you have one log on each side, we could do what we did when we did solving exponential equations, where we dropped the base. When we had the same base on each side of the equal sign, we drop the base, right? Here, if you have one log on each side of an equal sign, and they're both base B, what you could actually do is you could drop the log and equate the exponents, or sorry, and equate the arguments. Okay, so if you've got log base B is equal to log base B, they're logs with the same base. I could actually get rid of those logs. I could drop the logs, and then I equate these two arguments. So P is equal to Q. So an example of this, like just a very basic example, if I gave you the log 2 argument of X is equal to the log 2 of 6, you would say, okay, this would be a case one. I've got a log on each side of the equal sign. They're both base 2. I get to drop those logs now and equate the arguments, and X would be equal to 6. And that would be my solution. Because if you take this X out and put a 6 in, the left-hand side is equal to the right-hand side. Case 2 is what we did up here. So case 2, you guys, these two examples are case 2. And basically what case 2 is you're going to have a log and you're going to have a constant. So constant is just a number by itself. So when we have a log and a constant, what we do is get out of log form by converting to exponential form. So this one here, you're in log form, and we've got a constant on this side. So you're going to do B to the power of Q is equal to P. Okay, so it's this case is we're going to have one log at the end, and we're going to get out of log form by going into exponential form. Is going to be this case. Okay, so there's a question, and let me just see. Okay, so for this exploration here, if you look at this, you've got 2 logs on the left-hand side, and you have a constant. How you know whether it's going to be case 1 or case 2 is going to be that constant. If you have a constant anywhere in your equation, it is going to be case 2. Okay, so this would be case 2. What we do if it's case 2 and you have more than one log on the left-hand side, we have to use our log laws to combine these 2 logs. So I've got log base 5 and log base 5. Let's combine those 2 logs. That would be log base 5. These 2 logs are being added together, so that would be the product law. So it would be this argument times this argument. So x plus 1 times x minus 3, and that is equal to that constant, which is 1. Okay. From here, We could simplify this. So let's simplify this argument. So we would get log base 5. This argument, you're going to FOIL this, or you're going to use the distributive property. So x times x is x squared minus 3x. I'm just going to do these two steps together. So negative 3x plus 1x, that would be minus 2x. And then 1 times 3 is minus 3. Okay, so case 2, remember, you're going to have a log is equal to something on the right-hand side here that's not a log. And once you get to this step, it's exactly like we would have done in these two class examples, right? What do we do here? We get out of log form by converting to exponential form. So 5 to the power of 1 is equal to x squared minus 2x minus 3. 5 to the power of 1 is 5, is equal to x squared minus 2x minus 3. This is going to be a quadratic, so bring everything to one side of the equal sign where your x squared is positive. So I'm going to subtract 5 from both sides, and I will get x squared minus 2x minus 8. Now we're going to be factoring. So you need to find what are the two numbers that multiply to give you negative 8 and sum to give you negative 2. So those two numbers would be negative 4 and 2, right? So negative 4 and positive 2. Those two would multiply to give you negative 8, sum to give you negative 2. And don't forget, you don't want to drop that 0, right? So don't drop the 0. Now we actually have two answers. So this answer, x is equal to 4, and this answer, x is equal to negative 2. One of these might be extraneous. So what we have to do is we have to check which one of these is the actual solution and which one is extraneous. How you do that is as follows. Remember from the last class, I told you that the argument can never be 0 or less than 0. So the argument must always be greater than 0. So what you're going to do is you're going to take these numbers and we're going to put them back into the original equation. So x is equal to 4 and x is equal to negative 2. I'm just going to write it here. X is equal to 4, x is equal to negative 2. If I put a 4 in here, I'm going to get log base 5 of 5, right? And that's fine. I could have an argument of 5. If I put the 4 in this log, I'm going to have 4 minus 3, which would be the log base 5 of 1. And that is allowed as well. So this x is equal to 4 is going to be my solution. This one here, if I put this negative 2 in this first log, I'm going to get a negative 1. You can't have a negative argument. So this guy's going to be extraneous. If I put the negative 2 in here, I'm going to get a negative 5. Again, it's extraneous. It only has to dissatisfy one of these logs. So for example, let's say the negative 2 worked in this log, but it doesn't work in here. This guy is still extraneous. If it just dissatisfies, like I said, one of them, then your answer is going to be, your answer will be that this guy is extraneous. That's our solution. So now what I want to do is we're going to verify this. Let's see where we have room. So you might have room for B to verify. So I'll just show you what our verify would be. Let's write our original equation, which was the log base 5 of x plus 1 plus the log base 5 of x minus 3 is equal to 1. So when we verify, we always verify the original equation, and this is what I'm going to verify. I'm going to verify that my answer is x is equal to 4. So whenever I see an x, I'm going to put a 4 here. This would be the log base 5 of 5 plus the log base 5 of 4 minus 3 is 1. Same argument, same base, that answer is 1. right? 5 to what power will give you a 5? That answer is 1. Whenever you have an argument of 1, your answer is 0, right? Because 5 to what power will give you a 1? 5 to the power of 0. On the left-hand side, I've got 1 plus 0. On the right-hand side, I had a 1. So verifying, we have to make sure left-hand side and right-hand side are equal, and it verifies. Left side of the equation is equal to the right side of the equation. Okay. If you put in that -2, it wouldn't verify, right? Because you wouldn't be able to solve if you have a negative argument. It would give you an error on your calculator because it's extraneous. Okay, flip your page and let's look at page 260. So we're just going to be doing both of these cases, case 1, case 2. If we go to class example 1 and you look at this, you have a log on both sides of your equation. So if you have a log on both sides of your equation, there's no constant by itself. This would be an example of case 1. What case 1 says is that if you have a log on both sides of the equation and they have the same base, you get to drop the logs and equate the arguments. This is a common log and this is a common log, base 10, base 10. I could drop my logs and I could equate my arguments. X squared is equal to 16. From here, I need to solve for X. So I'm going to raise this to the power of 1/2. And I'm going to raise this to the power of 1/2 to give me X is equal to the square root of 16. X in this example is equal to plus or minus 4. And actually, maybe I should have showed it this way because it's a squared. X squared is equal to 16. To get rid of a square, you'd be square rooting. Whenever we square root both sides of an equation, we apply the square root principle, which states that the answer is positive and negative. So I'm going to write these two answers down. X is equal to 4. X is equal to -4. They may both be solutions. One of these could be extraneous. We have to check by plugging it back in our answers into the original equation. So if I put a 4 in, right, 4 squared is 16. Log of 16 equals log of 16. Left side equals right side. I know that X is equal to 4 is going to be a solution. Some students want to take this negative and they want to say, oh, this guy's going to be extraneous. But watch what actually happens. If I input that -4 into an X, whenever you input a number into a variable, you must input that number in a bracket. So how it would be correct is log of -4 squared. This would be -4 squared is 16. So if I input a -4 there, my argument is still 16. So that means that this is also a solution. I actually have 2 solutions here. And the reason is because even though this X is negative, my argument, once I square it, is going to be a positive number. So this guy has 2 solutions. Let's look at this one. We've got a log on each side of my equal sign, and I don't have any constants by itself. This would be a case 1. I need to, if I have a log of the same base, I will be able to drop my logs. But remember, we always have to isolate the log. This log is not isolated. There's a 2 in front. So get rid of that 2 by using the power law and putting it on top of the X. That would give you the log of X squared is equal to the log of 16. So then you'd say, okay, this is log base 10, log base 10. I got a log on each side. I could drop my logs and I could equate my arguments. X squared is equal to 16. And then you're like, okay, wait a second. I'm at the exact same spot that I was here. Okay, so you are, which is fine. Let's just keep going. Get rid of the square by square rooting both sides. X is equal to plus or minus 4. So I have 2 answers again, the exact same 2 answers. X is equal to 4 and X is equal to -4. Now, in this example, though, one of these would actually be extraneous. And the reason is you always have to input it back into the original equation. So if I put this 4 here, I will have 2 log of 4. This is totally fine because that argument is positive, right? You can't ever have a negative argument. However, if I input this guy back into the original, right? It has to go into the original. It would be 2 times the log of -4 is equal to the log of 16. In the original equation, if you have a negative argument, it has to be extraneous. I cannot have that. Even though you might say, well, can't you just put that to use a power law and put it on top of the argument? Yes, you can if you were solving, but we're not even going to solve with this because we can never have a negative argument. Therefore, this -4 in this example is extraneous, and this is my solution. Okay, so always just input your solutions into the original equation, must always go back into the original. If ever you get a negative argument, the answer will be extraneous. Okay, now let's flip to class example 2. Okay, in order to figure out case 1 versus case 2, if you only have logs, so if I look at this one, I've got a log, and a log. I don't have any constants by itself. This will actually be a case 1. This guy here, as soon as you have a constant somewhere in your equation, it is going to be a case 2. Okay, so for a case 1, we need logs on both sides of the equation, and then we're going to drop the logs and equate the arguments. But for here, if I've got 2 logs, combine these by using your laws of logs into 1 log, right? So log base 4, log base 4, this is subtraction. So what we are going to do is, it's the quotient law. So this would be the log base 4. This argument goes on top in my numerator, and this argument is in my denominator. And I'm actually going to put this in a bracket to show that this is my argument, right? Is equal to log base 4 of 8. So now for case 1, once you have a log on both sides of your equal sign and they're the same base, they will always be the same base. So they'll never try to trick you by having different bases or something like that. You get to drop your logs and you equate your arguments. X plus 1 over 2x minus 3 is equal to 8. Okay, I'm going to get rid of this denominator of 2x minus 3. I don't want that guy there. So to do that, I'm going to multiply this side by 2x minus 3, and I'm going to multiply this side by 2x minus 3. This will cancel, and I'll be left with x plus 1 is equal to 16x minus 24. We need to solve for x, so I'm actually going to subtract this 1x over here. That would give me 15 x's. I'm going to add 24 and join it to this 1, and I would get 25. Divide this side by 15 to isolate your x, and we're going to get x is equal to 25 over 15. Let's reduce that. 5 goes into 25 5 times, and 5 goes into 15 3 times. My answer is 5 over 3. I would need to verify to make sure that this isn't extraneous. So to make sure that it's not extraneous, you would put these back into the original equations. So 5 over 3 plus 1, that's going to give you a positive argument, right? 5 over 3 plus 1 will give you a positive argument. This one you might need to check. So 2 times 5 over 3 minus 3. So let's just quickly check that one, make sure that 2 times 5 over 3 minus 3. It gives me a positive number. My argument is positive. So that 5 over 3, it satisfies both of these logs, it will not be a negative argument. That means that that is the solution. Okay. Okay, this one right here.
Sorry,
yeah, go ahead.
I have to go now.
Yeah, no worries, Roger. Good luck on your exam.
Okay, thanks. See you.
I'll upload this video after. Okay, so for this one right here, if you have a constant, you want to get this isolated on one side, right? So I always want my constant positive. So I'm going to keep that constant there. I'm going to get rid of this negative log base of 6 x plus 3. I'm going to get rid of that by adding that to this side. So add that log to each side, and then I'll isolate my constant. So for these, you always want the logs, when it's a case 2, always have your logs together. So it would be this log. I'm going to add this log over to the left-hand side. That is equal to 1. Now what you need to do, say to yourself, how do I join these two logs together? You're going to join these two logs together by using your laws of logs. This would be the product law. Bases are the same in both logs, so multiply these arguments. And it would be x plus 4, x plus 3. This would give me log base 6. Right here, it would be x squared plus 3x plus 4x would be plus 7x, and then plus 12. In order to get out of log form, you must go to exponential form. So you're always doing this. The base raised to that power is equal to that, is equal to the argument, x squared plus 7x plus 12. Okay, 6 to the power of 1 is just 6. I'm going to, this is going to be another quadratic, so I'm going to subtract 6 from both sides. 0. X squared plus 7x plus 6. What gives you a product of 6 and a sum of 7? That's going to be 6 and 1 would be your answer. You must still not drop that 0, right? You could put the 0 on the left-hand side if you wanted to. It doesn't really matter. At this stage, you could just solve though in one step. This x is equal to negative 6. This x is equal to negative 1. Okay, we have two solutions. Both are negative. That's fine. We just have to check, are both of these solutions, or is one a solution or is neither of these a solution? So you go back to your original. And if I check the negative 6 first, negative 6 plus 4 is negative 2. So I don't even need to check this one. As long as it dissatisfies one of your logs, that negative 6 is extraneous. It would be extraneous here too, right? Because it actually dissatisfies both of these logs. Negative 6 plus 3 is negative 3. So that negative 6 is extraneous. So I've got to state that. I'm thinking that this one's going to be the solution, but I need to double check. So if this guy's negative 1 and this guy's negative 1, this argument would be a 3. This argument would be a 2, and I'm good. So that is my solution. That would be my answer. I'm going to tell you the most common mistake that students make when it is a case 2, and guaranteed you're going to have a case 2 that you'll be solving, more than one case 2 on your exams. What students do is once they get, everybody sort of gets to this step and they always get to here correct. Then they just forget about this base, like raising it to that power. And for whatever reason, students just write this argument like I have here, and they let it equal to 1. Like they just forget about this. You can't do that. Always tell yourself when you're writing your exam, to get out of log form, you must go into exponential form. you will see when you open up any key of mine, I always do this. And the reason why I draw that little arrow is just because I never want to forget that and make that mistake of equating this to 1. And I'll tell you right now, probably a third of you on your test will do that. Just a simple mistake. And then from here, all of this would be wrong. If it is an answer out of 4 and you do that, you get to here, you would be getting 1 out of 4. Okay, so to get out of log form, you always must go to exponential form. Okay, let's do class example 3. And I actually don't like class example 3 because it's a mess of a question. So we're just going to, I want you to cross it out and I want you to write this guy in. So log base 2 of 2 plus log base 2 of x minus 5 is equal to 5. There's 2 ways that you could solve this question. But so for example, some of you would see, oh, log base 2 of 2, that's equal to 1, right? And then if you could subtract 1 from both sides and you get a 4 here, and then, you know, you'd go 2 to the power of 4. So that's one way you could do it. The other ways we could do, you could look at this and you could say, okay, this is going to be a case 2. This is a case 2 because I have a constant. So I'm going to combine these 2 logs. And the logs are the same base, so I could use the product law by multiplying the arguments. So it would be 2 times x minus 5, and that is equal to 5. This would be the log base 2 of 2x minus 10 is equal to 5. From here, you are in log form. You need to get out of log form by going into exponential form. So write that, get out of your log form by going into exponential. Two to the power of 5 is equal to 2x minus 10. 2 to the power of 5 is 32, is equal to 2x minus 10. And then, just want to make sure I'm doing this right. Add 10 to both sides. 42 is equal to 2x. And then you would divide 42 by 2 to isolate your x, and you get x is equal to 21. Okay. You would get this exact same answer, or I'm just going to check this, but if I put 21 in here, that's fine because my log or my argument is going to be positive, so that's going to be my solution. And again, the alternate way that you could have solved this one is some students would have recognized that that's a 1, right? 1 plus log base 2 of x minus 5 equals 5. They would have subtracted 1 from both sides to get this guy is equal to 4. And then you would have done 2 to the power of 4 minus 2 to the power of 4 is equal to the argument. Okay, and you get the exact same answer. We have one more class example, and then I will give you your homework for this lesson. So just ignore this right now. It is this class example here. Solve this equation. And this, remember, was a log within a log. We did this very early on, but we'll go through this once more. So log base 2, the argument, this is my argument. Okay, so you have one log here, right? Because you have to recognize that this is the argument, is equal to a constant. So this would be a case, which case was this? This was case 2. And I could get out of log form right now by going into exponential form. So 2 to the power of 1 is equal to my argument. My argument just happens to be another log. Log base x of 3x plus 4. Okay, I've got a log equal to a number. Get out of log form again by going into exponential form. that would be x to the power of 2 is equal to the argument. Now you're going to be solving for x because you have a square. This guy's a quadratic. Bring everything to one side of your equal sign, and which would be x squared minus 3x minus 4. That is equal to 0. Find what gives you a product of -4 and a sum of -3. That would be, what would that be? -4 and +1. I'm just going to double check. -4 plus 1 is -3. -4 times, yep, -4 there. Okay, now we could solve. X is equal to 4. X is equal to -1. And then from here, we would have to verify. And it's actually it's not quite a bit of work to verify, but remember, we're always verifying in the original. And I'll show you how you would do that. So this original here, okay, so let's write this. So log base 2, the argument would be log of 4. So if x is 4, log of 4. And then if x is 4 here, it'd be 4 times 3, which is 12. 12 plus 4 is 16. And that guy's equal to 1. This is acceptable because I could actually solve what log base 4 of 16 is. Log base 4 of 16 is going to be 4 to what power would give you 16? The answer is 2. So this would be the log base 2. My argument would be 2, and that's equal to 1. Look at this. 2 to what power would give you 2, or same base, same argument. Log base 2 of 2 is equal to 1. 1 is equal to 1. So that one verifies. So I know that x is equal to 4 is a solution. Now I'm going to check this -1. And there's something's going to happen with this -1. So I'm just going to write it on this side. If I enter the -1, I'm going to have log base 2. I'm going to have my argument would be the log of -1. This guy would be 3 times -1 plus 4. So 3 times -1 would be -3 plus 4. That would be -1. Or no, that would be 1. And then that is all equal to 1. So when students write this, here's a mistake that sometimes students will make. And students will look and say, oh, this argument is positive, therefore -1 is going to be a solution as well. What happens though, when we first did the first lesson on logs, and we said that the argument could never be negative, we also said that the base of the log could never be a negative number. Okay, so this, you've never done a log with a negative base. So the base always has to be a positive number. And because of that, this -1 would be extraneous. So this guy's extraneous, it's not a solution. And again, the reason is because the base is negative. The base must always be positive. Okay, so that is the end of the lesson. I'm going to give you your homework so that you could circle this. So here's your homework right here, page 263. You might just want to flip. Circle 1, B, and C. Circle number 2. Circle 3, B, C. Circle 4, AC. 6B, and 7AC. On your exam, for your long answer, you're going to have a solving logarithmic equation. It'll either be a case 1 or a case 2. So you have to know both of these, and this will be all your practice. There are 3 podcasts, which are these 3 here. The only thing that I want to caution you about these podcasts is he explains it in a different method than I do. So what I sort of tell students to do is for these three, you have these questions in your podcast note package. What I would do is I would try to solve these questions without watching his video, because the video, like the way he explains it, might confuse you because he doesn't talk about this case 1, case 2, and he does just a totally different method. He arrives at the same answer, but does it a different way. And then you could just you could open up the video, fast forward to get the solutions. Okay, so just try to do these three on your own. I'm just going to stop the recording.